About a year ago, I finished my Golang authentication service called Amber. I currently use it on my website, however the code itself is rather big and clunky, and adding new features is a lot of busy work. Since then I've been prototyping a new paradigm for web design, and I'm ready to put it to the test. So I hope you'll join me in this series as I recreate Amber, from scratch. So what is this new paradigm I keep hyping? Well, first let's examine the old paradigm and understand its shortcomings. Amber Classic uses a layer structure. On top we have the handler layer, which parses data from the web request. Next we have the validation layer, which validates that data. Underneath is the controller layer, which processes and converts the data as needed. Finally, we have the data layer, which performs operations on the database. At first this system seems effective. Each layer is responsible for one type of task, which is an implementation of the separation of concerns software design principle. However, when you examine it further, you'll see a large coupling problem. Each layer is strictly bound to the layers below it. Therefore, if you wanted to reuse a layer such as validation, you cannot easily separate it. My new paradigm, by comparison, uses essentially the same structure, but stretches it out so it is long instead of deep. Layers are renamed nodes, and there's a separate object responsible for moving the data through the pipeline, or as I like to call it in the code, workflows. The control object will feed the output of one node into the input of the next, as well as handle any errors from the nodes. Now each node is responsible for itself and only itself. It does not concern itself with where the input comes from, nor how its outputs or errors are handled. Hope that all made sense, and if not, don't worry. The power of workflows will become more apparent as we dive into the code. Starting off, we make the obligatory Hello World program. We'll create a new Go module with the path to the repo on the Binary Soup GitHub account. This project is entirely open source and the repo link will be down in the description. Giving the project a run, and the world has been successfully greeted. Next we create a few directories and finally the Go file for the node definition. We define a new type called node of type interface. It will contain one method called run, which takes an input of any type, and returns an output of any type and an error. If you haven't used Golang before, the syntax may seem a little foreign, but you'll catch on pretty quick. Next we'll create the workflow definition. A workflow is defined as a slice of nodes, and we'll create a helper method for creating a workflow using Go's Veridic function syntax. Lastly, we create the run method for the workflow with the same signature as the node definition. We iterate for each node in the workflow, and for each iteration, we run the node and store the output variable and the input variable. We break the loop on an error, and return the file value of input and any error. And believe it or not, this is it for the core workflow structures. Back in main, we create a test workflow with no nodes. In this case, the workflow will simply return the input. In the main method, we pass a string variable as the input to the workflow and simply print the output. Now I actually ran into a few version errors here and had to update the Go version in my environment and the Go.bat file, after which everything was functioning. Next we'll start on our first model, the user. We'll create a new folder for the user files and create the user.go file. First we'll define the user model of type struct and give it two fields, username and password. However, we don't want to store the password in plain text, so let's change it to be a password hash instead with type byte array. If you're unfamiliar with hashes, they are essentially one-way or trapdoor functions. It is relatively effortless to obtain a hash from the plaintext, but very difficult to obtain the plaintext given the hash, perfect for password encryption. Now we'll create create.go in which we will define the create workflow for users. The function syntax is identical to the test workflow in main. Next we define a new struct called createUserInput. This struct will act as an input object to the workflow, and its fields will once again be the username and password. However, this time we do want the password to be plaintext. To convert our input to the user model, we create a new file called converter and define our first node. Note I use lowercase here to indicate that this object should not be exported from the user package. We used uppercase with the input struct as we do want a definition to be accessible in the main file. Now we implement the node's run method. In the function body, we type assert the input as our input structure. Next, we'll quickly add a helper method to create a new user object. Note that the return type is a pointer to a user struct. The reason for this pointer will become more apparent later in the project. Back in the converter, we call our helper method, pass in our username, for now nil for the hash, and return no error. To hash our password, we will employ the bcrypt algorithm provided by the crypto library. We pass in the password, cast it to a byte array, and use the default cost. If there was an error, we return a nil output and the error. However, I want to add more details to the error object to give more context in which it occurred. To achieve this, we create a new error.go file, move it to the correct directory, and define the function chain error. This function accepts the message and an error, and simply creates a new error with the message preceding the original error. Can I say error enough times? Now back in the converter, we call a function that adds some additional messaging. Now back in main, we create our input struct using a creative username and a very secure password. We'll replace the test workflow with a call for a new create user workflow and handle any errors by calling log fatal, which logs the error and exits the program. Finally, we print the output. Giving a run, we see it simply returns our input structure since our workflow is still empty. To run this, we simply need to instance our converter node. Now when we run, we see the output contains the username and the password hash as opposed to the plain text. The next step is to add validation to our workflow. For this, we create the validator.go in the user directory and define our validator node. For now, we'll just return the input and no error. We add the node to the workflow above the converter node and run the project to make sure it still works. As for the actual validation body, we first validate the username length. However, we don't just want to return the first validation error, but all the errors. For this, we create a slice of string and append the message string. The next length check is for greater than 30 characters. We will use an else if since the username can't simultaneously be shorter than the min and greater than the max. Password validation should validate the password is sufficiently complex enough to be secure. The first part will check for at least 8 characters. To check the password contains a digit and a symbol, we can employ regular expressions. Now rechecks is a bit of its own rabbit hole, but essentially we search the string for the desired characters, and if none were found, we create the error. For the final return, we simply join our errors together into a single error object. However, there's actually a bug here, so see if you can spot it before I fix it a little bit later. Back in main, running our program, we see that 2 validation errors are being returned. We can also change our input to test the other types of validations. However, when we use a valid input structure, the workflow still returns an error, although with no text. So, did you spot the bug? In our validation code, we always create a new error from the slice without actually checking if there were any errors to begin with. To mend this, we simply check the length of the slice before joining our strings. If there are no errors, then the flow follows through to the last line where we simply return the input and nil error. Back in main, giving it a run, and the bug has been fixed. Now the next logical step would be to actually save the user model to some form of database. However, this takes a fair bit of work to set up and get right, plus I want to do something special with the data logic. So for now I'll leave the workflow as is and we'll tackle the database logic in the next Amber devlog. That being said, there is one last topic I want to implement for this devlog. Now I've mentioned that Amber is a web service, yet we have yet to do any web stuff. Currently our create workflow only works if we call it through code. We'll start by creating a new workflow function called create endpoint. Now inspecting the workflow definition for a bit, you may realize that the run method is an exact match for the node interface, and therefore, workflows are in themselves a type of node. Or said another way, we've essentially implemented sub-workflows for absolute free. So back in the endpoint workflow, we can simply call the create workflow function and use it as a node. Then to make it work as a web endpoint, we only need to parse the create user input from the web request before the node, and send the web response after the node. All the actual hard work done by the workflow can be completely reused. Now, maybe you think I'm overhyping this a bit, but honestly I think this is so cool, and it was at this moment during my prototyping that I realized I was onto something with these workflows. Back in main, we'll delete the function body and create a new server instance. We'll use port 8080 and set the handler to nil for now. We'll print the address for servers running on for convenience and finally start the server. Now we'll need a router to tell our server where to send requests. Go has a fantastic sender library for HTTP tasks, but I personally like using the Julian Schmidt router. In the function body, we create a new router and return it. We'll add a new route for the post method on /user. For its handler, we'll add a new web package to the project and the file handler.go. Here we'll define a handler struct that contains a workflow object. For convenience, we'll also add a creation method. The handled method will have the following structure: response writer, pointer to the request, and the params. The function name itself is actually not important, so I choose to call it serve. Now we've actually encountered a bit of a shortcoming with our current workflow definition. Currently a node can only have a single input. However, we need a way for the free function parameters to be available in both the request parse node and the web response node. To solve this, let's add a context parameter to the node interface, which we can use to store additional data that is needed for the whole workflow. Originally I used type any, but I will change this a bit later. Modifying the node interface definition will also require updating all its implementations, so let's do that too. Note if a node does not need the context parameter, we can simply use an underscore. Next, let's create the context.go file in the web package and define the web context struct. The struct will hold the free handler variables from before. Back in the serve function, we first create a new web context. We'll run the handler's workflow using the context and nil input, since everything the first node needs is in the context object. Finally, we'll check for an error and return some form of error response. To achieve this, we'll create another file, response.go. In it, we define the error response struct with two fields, success and error. We'll also use Go's special struct tags, which we'll need when we later encode this struct as a JSON string. We'll also take this opportunity to define the data response struct we'll need later. This struct has two fields, success and data of type any. With the response structs defined, we now need the actual logic for sending a response. We'll create an internal helper method called sendJSONResponse, which takes in the response writer, the HTTP status code, and the actual data. To send the response, we first need to set the content type in the header to JSON, and write the header with the status. Next, we create a new JSON encoder, and tell it to encode to the response writer stream. Finally, we encode our data. Technically, this method throws an error, but this isn't an awkward place to handle errors, and we can actually be confident that an error should never occur here. We'll also create a helper method for sending an error response. This function will use the HTTP status bad request, and convert the error object to a string using the error function. While we're on the response train, let's also add the node for sending data responses. In a new file, we'll create the struct definition and the familiar node definition. Now it's at this point that I decided to change the web context design. We move the context file into the nodes package and rename it to a more general workflow context. Now to the node definition, we'll change the type any to simply workflow context. Once again, we'll need to reflect this change everywhere, so let's speed through that. Finally, back in the response node, we call our helper method giving it the response writer, OK status, and create a new data response object using our input. And that's actually all the logic we need here. To end off the function, we'll return no output and no error. Back in the handler method, we can now finish our error check by replacing the comment with a call to our error response helper. Back in the create endpoint, we can finally replace the bottom comment with an instance of our new node. With that, we have one last task to address to get our endpoint up and running. Home stretch, guys. We create a new file called JSON body parser and create a new node implementation. We start by creating a new JSON decoder and passing in the body stream from the request and the context object. Now we'll need an object to parse the data into, so we'll go up a few lines and create a blank input struct. Unlike encoding, we definitely need to check the error here. For the message, we'll use a generic invalid body string. To end the function, we return our parse model and no error. Although you might notice some issues with this approach. First of all, we want this method to be generic and not just for users. Also, trying to import the user package throws a cyclic dependency error, since the web package imports user and the user package imports web. To amend this, we can use one of Go's newest and coolest features, generics. This again is its own rabbit hole, but simply put, this feature allows you to add additional type to an object. In this case, we add a model type to the node and access that type in the function body to create a new instance of it. Now in the endpoint method, we can instance a new parser node and assign it the type of createUserInput. With all that complete, we are almost there. Back in main, we can create a new handler and pass in the workflow method. The router expects a function pointer here, so we also need to specify the serve method. Now let's get the server a test. Running the program, we can see that our server is started. To send a request, there are a few options out there, but for simplicity, we'll use the curl utility for now. In a new terminal tab, we'll invoke curl with the post method and the address localhost at port 8080. Our data is a JSON string which has the following format. Executing throws a 404 error because I forgot to actually specify the route. I'm ending that and we get no response, which probably means an error occurred. Inspecting server output, we can see a type assertion failed. The bug here is that the new method in our parse node creates a pointer to the struct, but our validator and converter nodes type assert without the pointer. To fix this, we can simply add the pointer to the assertion. After restarting the server, we can try our request again. This time we see that we actually got a response. Success is false, indicating an error, and the error complains of some validation issues. If we adjust our input so that the fields are valid values, we receive a success response with the user model as the data field. Very, very cool. Although you may notice we're returning the password hash as it's part of the user model. However, this field is sensitive and should only stay on the server. To amend this, we can create another converter node to convert the user model to a response object. In the user directory, we create a new file and define the user response struct. This struct has only one field, username, and we will also add the JSON struct tags. Below, we'll create another node and implement the very familiar run method. In the body, we type assert the input as a user model and simply return a new user response by copying over the username field. Finally, we instance the node above the response node in the workflow. Note for the change to apply, we need to restart the server. Sending a request one last time, we see our new converter is working. And with that, we finally reached the end of this devlog. Hopefully that wasn't too all over the place, but there is a fair bit of foundational code required to get this project off the ground. But with those core structures now implemented, hopefully over the next several videos we'll start to see just how reusable they are, and how much less effort it takes to make new workflows compared to the first one. As stated earlier, we'll tackle the database code next. Honestly, I have a really cool system designed for this and I'm excited to share it. Hope to see you there, and as always, take care and happy coding.